as I mentioned before, some of the situations where gases deviate from the behavior predicted by the ideal gas law are principally related to situations where the gases are under high pressure. And this is due to two main effects. So, one is that the assumption that gases take up basically no space and that the volume of a gas is basically all empty space becomes less accurate as you get to higher pressures. So, if you take a certain number of gas particles and they're at a relatively low pressure, they're going to exist in a relatively low density. Whereas if we compress them at higher pressure, that same amount of space taken up by the gas particles will now exist within the total volume of the gas, which is now much lower. And so at higher pressure, the volume of the gas particles is much more significant, and the assumption that they basically take up no space is violated. Additionally, at higher pressures, we have the fact that gas particles are essentially going to be pressed in closer together and pressed into each other essentially with more force. And so the fact that when gas particles get really close together, there are in fact some attractive forces, unlike what you would predict based on the ideal gas law, this also becomes more significant. And so the attractive forces between between gas particles at higher pressures also becomes more significant and can no longer be accounted for correctly by the ideal gas law. So to correct for those two phenomena, we have an equation called the van der Waals equation. I am going to show you this equation, but it's not because we're going to use it. It's only because I want to show you why we're not going to use it. And that's because it looks like this. It is extremely complex compared to most other formulas that you will have encountered in this class. There's a lot of variables going on there. You can see that volume shows up in two separate parts of the equation. It's just a mess, honestly, so we're not going to use this equation. Just be aware that there are certain situations where the ideal gas law really doesn't describe the behavior of gases all that well, and it's chiefly due to situations where there are high pressures and to a lesser extent where the temperatures are low. So moving on from that, let's talk just a little bit about the Earth's atmosphere. So, as you know, probably at least, the atmosphere of Earth becomes essentially thinner and thinner as you get to higher altitudes, and that's because the pressure of the gas decreases. And you're probably familiar with this if you know anything about, say, mountain climbing, where if you climb a mountain, especially a really high mountain, it's possible that you might actually need to take a supply of oxygen with you, and that's not because the amount of oxygen as a proportion of the total amount of gas in the atmosphere changes. In fact, it stays more or less constant through pretty much any altitude of the atmosphere, but just due to the fact that the amount of gas overall is lower at higher altitudes because the pressure of the gas decreases. Now, it turns out that there's no clear boundary between where the atmosphere of Earth stops and the vacuum of space begins. It's kind of a fuzzy boundary, but for a couple of reasons. One, because it's just a nice round number, and two, there are actually some kind of advanced physics considerations for the cutoff. It's generally said that Earth's atmosphere goes up to about 100 kilometers in altitude before you reach space. And you can see on the graph on the right some of the different regions of the atmosphere labeled. So there's the troposphere at ground level up to a little bit less than 20 kilometers. Above that is the stratosphere, above that the mesosphere, and further above that still the thermosphere, and eventually you reach space above that. Now, one important phenomenon that goes on in Earth's atmosphere is referred to as the greenhouse effect. Now, this is a often sort of misunderstood effect, even if people realize that this is what's responsible for helping keep the Earth at a warm enough temperature to essentially sustain life and have liquid oceans and all that good stuff. So, As it turns out, the composition of the atmosphere is about 78% nitrogen, N2, about 21% oxygen, O2. So, if you didn't already know, most of the atmosphere is actually nitrogen and not oxygen. Oxygen is only about a fifth of the uh, composition of the atmosphere, even though it is what you use for respiration. So together, those make up about 99% or so of the atmosphere. Most of the remaining gas in the atmosphere is actually argon, and for these purposes, we're ignoring water vapor. The amount of water vapor in the atmosphere varies from basically 0% over, say, the Sahara Desert up to several percent in, say, the region over a tropical rainforest or something. So we're going to ignore the composition of the atmosphere that's due to water and just look at all the gases that exist here for the dry atmosphere with all the water removed. So nitrogen and oxygen together about 99%. Almost all the remaining gas is actually argon, which exists not as molecules like N2 or O2 do, but just as individual argon atoms since it's a noble gas. And that's almost all of the remaining 1% of the atmosphere. However, besides those three gases, we actually have a fourth gas, which is about 400 something parts per million at the time I'm recording this. So about 400 out of every 1 million molecules, pretty low percentage, is a gas called carbon dioxide, CO2. We've encountered that before in this course. And it's actually carbon dioxide and water as well that are responsible mainly for the greenhouse effect. So, as you see in this diagram, UV and visible light are emitted by the sun, and most of the UV radiation gets absorbed by the upper levels of the atmosphere. That's actually one of the things that the ozone layer is really important for. Now, visible light mostly makes it to the surface of the Earth, and it may surprise you to know that the sun actually doesn't emit all that much infrared radiation. We think of the sun as warming, so you might assume that it emits a lot of IR radiation, but actually most of it is just UV or visible light, and there's comparatively little infrared radiation given off by the sun. So not much infrared radiation reaches the Earth from the sun. Now, as the Earth is heated up by the sun, anything that has a temperature at all, really, emits radiation, and the wavelength of that radiation is determined by what the temperature is. So, at temperatures near, say, room temperature, the temperature of the Earth, body temperature, the wavelengths of light given off are in the infrared portion of the spectrum. So the wavelengths that are somewhat longer than red visible light. Now, gases like nitrogen, oxygen, and argon don't absorb infrared radiation at all. And so those gases on their own just simply allow the infrared radiation to come off of Earth's surface and just pass directly into space, more or less. Water vapor and carbon dioxide actually can absorb some of that infrared radiation, and they can re-emit that radiation either back towards the surface of the Earth or back into space. So the net effect is that some of the infrared radiation that comes off of Earth's surface actually gets bounced back down into the Earth's surface by being absorbed by carbon dioxide or water vapor, and some of that infrared radiation escapes into space. Now, the amount of water vapor in the atmosphere is actually something that more or less just depends on the weather, and it's not something where humans can put more water vapor into the atmosphere in a way that will really keep that water vapor level at a higher level, because water is basically a liquid at room temperature, and so what water vapor that does exist in the atmosphere is just due to weather phenomena. However, carbon dioxide is a gas at pretty much all temperatures anywhere on Earth. I guess it could actually be a solid in Antarctica, but for the most part, carbon dioxide is always a gas. So if you emit carbon dioxide into the atmosphere, it stays there as a gas. And so if we increase the amount of carbon dioxide in the atmosphere, as has been happening over the past century or so, perhaps a bit longer than that, it's going to increase the effect of the greenhouse effect. As a result, we would expect the temperature of Earth to warm as a result of that increased greenhouse effect. And actually, the increased greenhouse effect warming the Earth actually causes more water vapor to exist in the atmosphere as it gets warmer, and so it's actually a compounding effect because the water further increases the greenhouse effect. As a result, carbon dioxide being emitted into the atmosphere and increasing over time. Before the Industrial Revolution, the amount of carbon dioxide in the atmosphere over the past several thousand years was pretty steady at about 270, 280 parts per million. But over the past century or so, it's gotten to the point where we're now well over 400 parts per million of carbon dioxide. So a pretty significant increase in the amount of CO2 in the atmosphere. So we have a stronger greenhouse effect on Earth that's developed over a much shorter period of time than has ever happened on sort of normal geologic scales. And so we're currently experiencing what's called anthropogenic global warming, because anthropogenic means that it's caused by humans, which it is. It's caused by human activities that release carbon dioxide, and methane is a lesser but still significant contributor to the greenhouse effect as well. Human activities also cause methane levels in the atmosphere to rise, and methane is also a greenhouse gas. Oxygen and nitrogen, as well as argon, which basically make up most of the atmosphere, actually don't contribute to the greenhouse effect at all. So it's just these so-called greenhouse gases that are responsible for the warming of Earth due to the greenhouse effect. And so we are, like I said, currently experiencing climate change, and there's no real, at this time, mitigation of the amount of carbon dioxide, methane, or other greenhouse gases that are being emitted into the atmosphere. So it's likely, and it is the consensus of climatologists, that much greater human action is needed to reduce both the amount of greenhouse gases that are continually emitted into the atmosphere, and probably to some extent we actually need to not only do that, but actually come up with ways to reduce the amount of carbon dioxide in the atmosphere back down to below 400 parts per million, ideally. And so some sort of action is needed there. That what exactly that is beyond the scope of something like Chem 1211, but it is worth mentioning. You can see here how carbon dioxide has changed over time, over the past, say, 150, 160 years. So like I said, before the Industrial Revolution, it was at about 280 up to about 300 parts per million. And then especially since the, say, 1960s and 1970s, it's really started to increase, where we're now, this graph stops at 2010, but here in 2020 we are definitely well above 400 parts per million. You can actually look up on Google, if you look for the Mauna Kea Observatory, they have continuous monitoring of the amount of carbon dioxide in the atmosphere, so you can get a live reading on that pretty much anytime you want to, just from the internet. Okay, so that brings us to the end of Chapter 10 and the end of the last set of lecture slides. So, as always, I would encourage you, if you have any questions about anything that we've covered here today, please contact me during my office hours, which are being held remotely. I'm recording this now before classes resume during the week of March 31st, so I'm not exactly sure what all the details of the remote office hours are going to be, but I'll send out more information about that via email if you haven't gotten it already when you're watching this. So remember to stay in touch, keep checking your email for updates, and stay safe and take care.